Ladies and gentlemen, welcome to a seventh video lecture about the Fivefold Sun project. This is October 8th of the year 2018, about 1 year after the book The Fivefold Sun, including 15 volumes, was filed at the Bibliothèque Nationale de France in Paris in late 2017. Today we deal with part 2 of this book, which focuses on the geometry of the solar ball in 3 dimensions. What we'll be looking for is symmetry in the solar ball. Is there any symmetry in this spheroid? Of course, we have ended the presentation of part 1 with the conclusion that the numerical kinematic of the differential rotation of the solar ball over a quasi-decadal so-called Schwabe cycle in the activity of the Sun can be represented by a sequence of Fibonacci numbers and other so-called generalized Fibonacci numbers. Because such numbers are representative of fivefold symmetry among numbers, we have a hint that maybe there is also, if there is any symmetry in the solar ball, a fivefold symmetry. We deal today in video number 7 of the Fivefold Sun with sections 1 and 2 of part 2, which we can title with the question towards an icosahedral constitution for the Sun. The entire part 2 is titled The Fivefold Constitution of the Sun. Of course, the word constitution here is an accepted terminology started in the 17th century and celebrated by also in the 20th century luminaries such as Eddington, who wrote about the constitution of a star in general, or of the Sun in particular. The word refers to a geometrical structure which would be in accordance with the physical laws that can be detected in this star. So part 2 deals with what we call the basic 3D geometry of the solar ball, as opposed to a 2D geometry of the surface of the Sun, which will be addressed only in the last part of this project, in part 6 of the Fivefold Sun. We have here a couple of interesting citations from famous astronomers about this interesting question of what would be a constitution for the Sun. Richard Carrington, who first described the time evolution and latitudinal evolution of sunspots at the solar surface, wrote that if the solar phenomena alone would be subject to caprice, this would be a big problem for any mind of philosophical training amid the, what he meant, universal subjection to order and law. Why would the Sun would be subject to caprice? We would say in modern 20th century terms, why would the Sun be a chaotic object or a random phenomenon amid the universal subjection to order and law? At least that was the impression of Richard Carrington. We shall see that if we look for symmetry, we have to refer to polyhedra, those solid objects that were first studied by the ancient Greeks. However, a very official institutional astronomer in the late 18th century, Jean-Baptiste Delambre, also in the early 20th century, in Paris, he wrote that polyhedra caused the famous Kepler to waste a lot of time and waste a lot of computations. Well, we shall see if this is relevant to the study of the Sun or not, as Mr. Delambre seemed to think. The entire contents of part 2, you see this is a rather dense part composed of several volumes, is as follows. In part A, we deal with fivefold symmetry in general until we arrive at the suggestion of a geometrical model in 3D for the Sun. And in part B, we look at possible observational evidence of such symmetry as proposed above in the solar ball's interior, in terms of radial fractions of the solar interior. In part 2C, we will again look for observational evidence, this time in the Sun's latitudinal phenomenology. In part D, a third kind of observational evidence is addressed, the longitudinal distribution of solar activity. Finally, we will also address the issue of the near-surface 3D geometry of the Sun. The contents of video number 7 today, they include the presentation of the basic findings of part 1 in terms of a fivefold symmetry in a nuclear kinematic, again, of the solar cycle. And end with a basic suggestion of an icosahedral model. So we start with the Heinz of fivefold symmetry in the numerical kinematic, where we found the Fibonacci sequence in terms of rigid solar rotation across the solar cycle, 55, 89, and 144. We also in the first part of the fivefold Sun made a comparison of the 144 rigid rotations and the altogether 144 possible colorings of the faces of the icosahedron. And with the number 144, which would be the square of the number of vertices of the icosahedron, which has 12 vertices. Then the number 60, it is the number of hemispheric laps, which we found to accumulate over one Schwabe cycle, laps of the equator compared to the pole of the Sun. The Schwabe cycle is half the Sun's Hale magnetic cycle. And we shall see that 60 is the number of elements of the icosahedral symmetric group. It's half the total number of elements of the full such symmetric group, and we will ask ourselves whether this parallel is meaningful or coincidental. So the 60 rotations that bring the icosahedron back to itself in terms of a solar spherical symmetry, which would be in accordance with icosahedral symmetry. They are the 60 leaps of the equator over the pole of the Sun over a Schwabe cycle, when the solar sphere, in terms of its magnetic structure, has a polarity reversal either at the poles during solar maximum or at the equator during solar minimum. It happens to be also the order of the rotational icosahedral group. 60 in terms of symmetry groups is the number of rotations that leave the icosahedron invariant. The rotational icosahedral group is composed of 60 elements. If we turn now to the so-called full icosahedral group, it has twice the number of elements. 60 times 2 equals 120 elements in the full icosahedral group. And in addition to the 60 elements of the rotational group as listed in the preceding page, we have again 60 operations, 60 elements, which are reflection elements, so-called reflection elements. The first element is the inversion. So we have a double set of 60 elements in the full icosahedral group. There is here a parallel with the icosahedral, between this icosahedral symmetry inversion leading in one set 60 symmetry operations, 60 elements of a symmetry, and in the second set by inversion and reflection 60 additional elements. This parallel is with the polarity reversal in the Hale cycle, which yields in the magnetic evolution of the Sun an additional 60 laps of magnetic lines of force in the solar ball. We now want to inquire whether this parallel is coincidental and meaningless, or maybe if it is truly a hint at the presence of a spatial fivefold symmetry in the Sun. Fivefold symmetry is the most complex symmetry that can be achieved in three-dimensional space, as shown in this typology. We shall see in a further step what is the relation between the polyhedra in general, the regular solids, and the symmetry groups. There are a number of regular figures which verify threefold symmetry as well. The tetrahedron, the cube, and the octahedron, plus the icosahedron and the dodecahedron, who also, by the way, verify twofold symmetry. If we now turn to fivefold symmetry, which is displayed in 2D by the regular pentagon, such symmetry is displayed in the only regular solid polyhedron, which has regular pentagons as its faces, which is the dodecahedron. But it is also displayed, verified, in the icosahedron, which is the dual of the dodecahedron. It is proven that no regular figure verifies n-fold symmetry for n of more than 5. In other words, we cannot have any more complex regular figure than those with fivefold symmetry, which we just mentioned, i.e. the dodecahedron and the icosahedron. We shall now have a look at a few of the regular solids and models of the dodecahedron and icosahedron. This is, of course, the cube. You see hexahedron in Greek, it means 6 bases. Today, nowadays, we say 6 faces. This is the dodecahedron. It has 12 faces. The faces are pentagonal, and it is in the pentagons of the faces that we find the ratio 1.618. Whereas its dual, the icosahedron, is also a fivefold solid. The symmetry of the fifth order is not to be found in the faces, which are triangular, but in the number of 5 edges that surround each vertex. As you see, we count 5 edges at this vertex and at any other vertex of the icosahedron. So these 3 solids, they also verify threefold symmetry and twofold symmetry. So the cube, unfortunately, does not verify fivefold symmetry, leaving these 2 regular polyhedra as the 2 only candidates to represent fivefold symmetry in a model of a sphere. We can now have a look into the natural world in a search for physical objects that might be verifying fivefold symmetry, which would be examples of natural things that are akin to a fivefold spheroid, as we assume that the Sun itself might be. In the world of astrophysics, there is no such a natural thing. There is no proven icosahedral or dodecahedral model for any astronomical object. Ancient Greeks, after Plato, believed that the universe perhaps was modeled after a dodecahedron or contained in a dodecahedral envelope. Recently, a team of astrophysicists tested this idea against modern-day measures of the shape and extension of the universe, and they found that it is not the case. It is in fact not the case in any astrophysical object in which it was tested. In macromolecular compounds instead, and in atomic clusters, there are cases, well-known, numerous cases of icosahedral symmetry or dodecahedral symmetry. Icosahedral symmetry is the predominant case. So, without going into the details of these compounds, we can make a note that there exist, in fact, in the natural world, some examples of natural things that indeed verify fivefold symmetry, and in which we can find icosahedral or dodecahedral symmetry. If we now want to check in a rigorous manner whether observational phenomenology in the solar ball matches any fivefold model, we have to perhaps make a choice of which regular solid we want to choose as our yardstick. If we compare now the icosahedron and the dodecahedron, there are 2 criteria against which the icosahedron will prove to be the better solution. First of all, it best matches the minimal surface of the sphere, better than the dodecahedron or than any other regular solid for that matter. And this is more crucial and is a key to our research and to our search. The icosahedron is the optimal spherical code, which the dodecahedron is not. Optimal spherical code in the case of the icosahedron for the largest number of points so far known. An optimal spherical code is an optimal configuration of points on the sphere so that the minimum distance between any two points is maximal. This is, it is interesting to note that it is a special case of the Thomson problem of 1904, which deals with the same issue for charges on a sphere. So for 4 points on a sphere, it is proven that the optimal code corresponds to the vertices of the tetrahedron, for 6 points to the vertices of the octahedron, and for 12 points to the vertices of the icosahedron. Each of these three solids is a deltahedron, i.e. it is a solid the faces of which are all triangles. The other regular solids are not optimal spherical codes, especially the dodecahedron is not a optimal spherical code. So the icosahedron, in fact, is the largest known optimal spherical code in 3D, which also is a regular symmetrical solution. So this special fivefold solid, the icosahedron, will be the model against which we will test the idea of fivefold symmetry in actual phenomenology of the Sun. This is the end of video lecture number 7 of the Fivefold Sun project. In video 8, we will go on and suggest a specific icosahedral arrangement in a sphere against which we will then try to verify whether actual solar phenomenology is verified along these lines. Thank you for your attention.